Hello everyone, welcome to my YouTube channel. I am Harshita from Sri Venkateswara College of Engineering. In this video, let us discuss about how to convert an Epsilon NFA to the DFA. Let us see what is Epsilon NFA. Epsilon non-deterministic finite automata or a type of finite automata on that an transition without consuming any input symbols. They are characterized by the presence of epsilon transactions along the automata to move between states without reading a character. Understanding epsilon NFA is the crucial for converting them into deterministic finite automata to simplify computational problems. Next, let us see what is DFA. A deterministic finite automata has a single unique stage for every input symbol from any given state. Unlike epsilon NFA, DFA do not have epsilon transactions, meaning they consume an input symbol to make transaction. DFAs are easy to implement in computer algorithm as their behavior is predictable and deterministic. Next, let us see the importance of conversion. Converting the epsilon NFA to the DFA allows for easier implementation in software application. DFA can be more efficient in terms of time complexity when processing input symbols. The conversation process ensures that the same language is recognized by both automata, maintaining equivalency. Next, let us see the epsilon closure. The epsilon closure of the state is the set of states that can be reached from the state using only epsilon transactions. Finding the epsilon closure is a crucial step in converting the epsilon NFA to the DFA. This closure helps in determining all the possible states that can be reached without consuming input symbols. Next, let us see the simple example of epsilon NFA. Consider an epsilon NFA which states Q0, Q1, Q2 and the alphabets, that is the input symbol 0, 1. The transaction include epsilon transaction from Q0 to the Q1 and Q1 to the Q2 along with regular transactions. The initial state here is the Q0 and the accepting state here is the Q2, that is the final state. Next, let us see how to draw the epsilon NFA. The epsilon NFA can be represented as the directed graph with the nodes and the edges. Nodes represent states while the directed edges represent transactions between these states. It's essential to visualize the graph for the better understanding during the conversation process. Next, let us see how to find the epsilon closure. The epsilon closure of Q0 is the Q0, Q1, Q2. Since epsilon transaction allow movement to all the states, the epsilon closure of Q1 is Q1, Q2 as it can be transaction to Q2 using epsilon. The epsilon closure of Q2 is Q2 since there are no epsilon transaction from Q2. Next, let us see the transaction table for epsilon NFA. A transaction table summarizes the states and the transaction for epsilon NFA. It includes both the epsilon transaction along the sidewise input symbol transaction. This table will use to systematically convert the epsilon NFA into DFA. This table has the present state, the next state of the when given 0 and the next state for one input given 1. We can see here Q0 is the initial stage and Q2 is the final stage. Next, let us see constructing the DFA states. Each states in the DFA corresponds to a unique combination of the states from the epsilon NFA. The initial state of the DFA is the epsilon closure of the epsilon's NFA's initial state. Subsequent DFA states are derived by combining or considering all the possible input symbols and their transactions. Next, let us see how to create the DFA transaction table. The DFA transaction table is built by examining the transition from each state to the new states. For each combination of the states in the Epsilon NFA determines where the transaction led under input symbols. This table will help in defining the structure of the resulting DFA. Here we can see the transaction table for the DFA from the above figure. We can see here the input states and the input symbols. Okay, here we can see the states are Q1, Q0, Q1, Q2, Q3 and Q4. As we can see that Q0 is the initial state and the Q2 and the Q4 are the final states. Next, let us see the example of the transaction table. For the previous Epsilon NFA, the DFA transaction table might include states like Q0, Q1, Q2 and the transaction based on the input symbols. Each entry in the table indicates the next state for a given input for the current state. This reflects the behavior of the original Epsilon NFA using the deterministic transactions. Next, let us see defining accepting states. Accepting states in the DFA are determined by the presence of accepting states in the Epsilon NFA. If any state in the DFA corresponds to an accepting state in the Epsilon NFA, it is marked as accepting. This ensures that the DFA recognizes the same language as the Epsilon NFA. Next, let us see the complete DFA construction. Once the transition table is complete and the accepting states are identified, we finalize the DFA. The DFA consists of all the unique states and their transactions based on the constructed table. This DFA will accept the same language as the original Epsilon NFA. Now let us see the example of DFA diagram. A diagram of the constructed DFA illustrates all the states and the transactions visually. This graph helps in understanding the flow of states based on the input symbols. It serves as a reference for verifying the correctness of the conversions. Next, let us see the properties of the converted DFA. The resulting DFA will have a finite number of states and transitions. It will operate deterministically, processing input strings without ambiguity. The conversion preserves the language recognized by the original Epsilon NFA. Next, let us see the complexity of conversion. The conversion process from the Epsilon NFA to the DFA can have exponential complexity in the worst case scenario. Understanding this complexity helps in accessing the feasibility of conversions. Finally, I conclude that converting Epsilon NFA to the DFA is the fundamental process in the theory of computation. It enhances the efficiency and the predictability of the automata used in a conceptual task. Mastering this conversion is essential for everyone studying automata theory. Thank you for watching this video.